Welcome, and thank you for joining. Today, we'll explore LeetCode problem number 1917. While the problem's details are unavailable, this gives us a unique opportunity to discuss general strategies for tackling coding challenges with limited information. Let's dive in. In this problem, we are dealing with a situation where the data for LeetCode problem number 1917 is currently unavailable. This means that the problem's description, metadata, and all the essential details like the input and output format, examples, and constraints are either unpublished or temporarily inaccessible. As a result, there isn't much we can do at the moment to analyze or solve this problem. Essentially, this slide is here to inform users about the issue and to advise them to check back later once LeetCode resolves it. With no input or output specifications provided, there's no further information to work with for now. Now, when it comes to examples for this problem, none are available due to the missing data. For instance, both the inputs and outputs for example 1 and example 2 are marked as unavailable, and no explanations can be offered in the absence of problem details. Similarly, no constraints have been defined, as the necessary data is missing. This also means that edge cases cannot be identified or considered at this time. Overall, the lack of information limits us from exploring or solving this problem until the issue is addressed by LeetCode. When faced with a problem like LeetCode number 1917, where the description is missing, we must adopt strategies to handle the ambiguity effectively. One such approach is reverse engineering based on related problems. The intuition here is that problems in numerical proximity on LeetCode often share common themes, patterns, or difficulty levels. For instance, if problem number 1916 deals with graph traversal, it's reasonable to hypothesize that problem number 1917 might involve a related concept, such as finding the shortest path or analyzing graph connectivity. To apply this approach, the first step is to investigate problems with similar numbers to identify recurring structures or themes. Next, we can develop hypotheses about what the requirements might be and test these by implementing solutions for related concepts. By validating these hypotheses with sample test cases or edge cases, we can refine our understanding of the potential problem. However, this method does come with trade-offs. While it provides a logical starting point, it can be time-intensive and carries the risk of incorrect assumptions if the problem turns out to be unique. Even so, it's a practical way to tackle the unknown when no concrete data is available. Another effective strategy is to use a generalized problem-solving framework. This approach is based on the observation that many LeetCode problems fall into well-known categories, such as dynamic programming, graph algorithms, or array manipulation. By designing a framework that tests these common problem types, we can systematically explore potential solutions. The process begins by analyzing the problem number and, if available, the difficulty level to estimate the complexity of the solution. Then, we create a framework capable of testing common operations like sorting, searching, recursion, or even dynamic programming on hypothetical input data. As we receive feedback from test cases, we can refine our assumptions and iterate on the solution. While this method ensures comprehensive coverage of a wide range of scenarios, it does have its drawbacks. It may lead to over-engineering or wasted effort on irrelevant operations, especially if the problem turns out to be simpler than expected. Nevertheless, this approach is invaluable when no specific details are provided, as it allows us to methodically test a broad set of possibilities. In situations like this, where problem details are completely absent, the most effective strategy combines reverse engineering with a generalized problem-solving framework. This hybrid approach leverages historical patterns from related problems while also systematically testing broad hypotheses about the problem requirements. By blending these methods, we can achieve a balance between efficiency and adaptability. The key insight here is that problem solving is inherently iterative. Even without explicit details, we can reduce uncertainty step by step by using data from similar problems and a structured framework. For instance, if surrounding problems frequently involve dynamic programming, we can hypothesize that this problem might also involve state transitions or optimization. The trade-offs between the two individual approaches are also important to consider. Reverse engineering alone is quicker but risks being inaccurate, while a generalized framework is thorough but can become overly complex. Combining these approaches allows us to mitigate the weaknesses of both, making the exploration process both efficient and comprehensive. Ultimately, the chosen hybrid approach offers a structured and logical way to navigate the ambiguity of a problem like LeetCode number 1917. By systematically combining insights from related problems with broad testing frameworks, we can ensure steady progress even in the absence of specific problem details. This strategy not only reduces uncertainty but also provides a reliable method for tackling similar challenges in the future. With this approach, we maintain a balance between exploring potential solutions and narrowing down the problem space efficiently, allowing us to work confidently despite the lack of concrete information. To begin solving any algorithmic problem, the first step is to thoroughly understand its requirements. Since the problem details aren't available, we start by hypothesizing what the problem might involve based on its context, such as its title, tags, or general patterns in similar problems. For instance, if the problem falls under numerical operations, we might expect tasks like array manipulations, matrix calculations, or arithmetic operations. On the other hand, tags like dynamic programming or graph theory can guide us toward specific paradigms, such as breaking problems into overlapping subproblems or exploring node relationships. Once we have a hypothesis, we move on to identifying the input and output formats. This means guessing whether the input is an array, string, or matrix, and determining what the output should look like, perhaps a number, a boolean, or a modified version of the input. At this stage, it's also critical to consider edge cases. For example, if the input is an array, we should account for scenarios like empty arrays or extremely large ones. Similarly, if integers are involved, we must think about cases like negative numbers or very large values. This foundational understanding sets the stage for developing a structured solution, even when the problem definition is unclear. The next step is to develop a brute force solution. This involves implementing a straightforward approach that directly follows the problem's requirements, even if it's inefficient. The goal here is not to optimize but to ensure correctness by covering all possible scenarios. For example, if the task involves finding pairs of numbers that satisfy a certain condition, we could use nested loops to test every possible pair. While this might result in a time complexity of O(n)(, it provides a clear starting point. Once we have a working brute force solution, the focus shifts to optimization. Here, we apply common strategies to make the solution more efficient. Sorting is a powerful tool for reducing the search space, often enabling techniques like the two-pointer method. Hashing can significantly speed up lookups, especially in problems involving frequent queries. Dynamic programming is another invaluable approach, allowing us to store intermediate results and avoid redundant calculations. For sorted inputs or problems with monotonic properties, binary search is a go-to method for achieving logarithmic time complexity. These optimization techniques transform an initial brute force solution into one that is both correct and efficient, paving the way for handling larger inputs and tighter constraints. After developing and optimizing the solution, it's time to rigorously test it with edge cases. This means verifying the solution against inputs at the boundaries of the problem's constraints, such as the smallest and largest input sizes, or against special cases like negative numbers, zeros, or duplicates, depending on the input type. The goal is to ensure the solution is robust and handles these less obvious scenarios gracefully. Additionally, the solution should be able to process invalid or missing inputs without crashing. Once edge cases are addressed, we can then generalize and refine the code. This involves confirming that the solution works for all valid inputs while maintaining its optimized performance. Refinement also means simplifying the code where possible to enhance readability and maintainability. Adding comments or documentation to explain the logic makes the solution easier to understand for others, or even for ourselves when revisiting the code later. This iterative process of testing, generalizing, and refining ensures that the solution is not only correct and efficient but also clean and professional. To summarize, solving algorithmic problems effectively begins with a structured framework. When the problem is unknown, start by hypothesizing its type and requirements, then progress by building a brute force solution to ensure correctness. From there, refine and optimize iteratively to improve efficiency without sacrificing clarity. It's important to prioritize clarity initially, as a clear solution is easier to debug and verify. Once correctness is established, focus on optimization to handle larger inputs effectively. Testing plays a critical role in this process, as edge cases often reveal hidden issues. Covering these ensures that the solution is robust in all scenarios. Some common optimization techniques you can rely on include sorting, hashing, dynamic programming, and divide and conquer approaches, which are versatile strategies for a wide range of problems. Additionally, understanding the right data structures for a given problem is equally important. Arrays are excellent for sequential data, hash maps excel in fast lookups, priority queues or heaps are ideal for managing extremes like maximum or minimum elements, and graphs are indispensable for traversal-based problems like shortest paths or connected components. These insights form the backbone of a strong problem-solving approach. Finally, let's discuss some key operations that frequently appear in algorithmic problem-solving. Sorting is a foundational operation that simplifies search-related problems by enabling strategies like binary search or the two-pointer technique. The two-pointer method, in particular, is highly effective for problems involving sorted arrays, such as finding pairs with specific properties. Recursion with memoization is another powerful tool, especially in dynamic programming, as it prevents redundant calculations by storing intermediate results. Binary search is indispensable for problems involving monotonic functions or sorted inputs, offering logarithmic time complexity. The sliding window technique is another optimization strategy, suited for problems involving subarrays or substrings, as it allows us to maintain a running window of elements without needing nested loops. Let's apply these ideas to a hypothetical problem, such as finding two numbers in an array that sum up to a target. A brute force approach would involve traversing all pairs to check their sums, leading to O(n)² complexity. However, we can optimize this by using a hash map to store complements, reducing the complexity to O(n). When solving such problems, always account for edge cases like empty arrays, single elements, duplicates, or negative numbers to ensure the solution is robust and reliable. Since the problem description for LeetCode problem number 1917 is unavailable, this Python implementation assumes a hypothetical problem involving an array. The problem we are solving here is to find the sum of unique elements in an array. For instance, given an array like 4, 5, 6, 5, the output would be 10 because the unique elements are 4 and 6. We begin by using a dictionary to count the occurrences of each element in the array. For every number in the array, we increment its count in the dictionary. Once we have the frequency of each element, we iterate over the dictionary to sum up the numbers that appear only once. This ensures that only unique elements contribute to the result. The solution class contains a single method solve, which takes the input array nums. The example usage at the bottom demonstrates how to instantiate the class and call the method with a sample input array. This approach has a time complexity of O(n), where n is the length of the array, since we iterate over the array twice, once to populate the dictionary and once to calculate the sum of unique elements. The space complexity is also O(n), due to the storage of the dictionary. This implementation is concise, efficient, and handles edge cases like an empty array or arrays without unique elements appropriately. Here, we begin by importing the necessary packages, specifically the hash map and map classes. These will allow us to store and manage the frequency of elements in the array. The solve method is designed to take an array of integers as input and return an integer result. Inside this method, we first initialize a hash map called count to keep track of how often each number appears in the input array. Next, we iterate through the array using a for each loop. For each number, we update its count in the map, either incrementing the existing value if the number is already present or initializing it to 1 if it's not. After populating the map with frequencies, we initialize a variable result to 0. This will hold the sum of all elements that appear only once in the array. We then iterate through the map entries. For any key whose value is exactly 1, we add that key to the result. Once this process is complete, we return the final result, which represents the sum of all unique elements in the input array. In the main method, we demonstrate how to use the solve method with a hypothetical input array. Here, the array 4, 5, 6, 5 is used as an example. The solve method is called with this array, and the output is printed to the console. Based on the logic we implemented earlier, the method calculates the sum of the elements that appear only once in the array. In this case, the numbers 4 and 6 each appear once, so their sum, which is 10, would be printed. This gives a clear example of how the solution works and helps us verify the correctness of the implementation. You can replace the example input with other test cases to further validate the program. To solve this problem, we begin by initializing an empty dictionary called count. This dictionary will help us keep track of how many times each number appears in the input array. As we iterate through the array, we process each number one by one. First, we encounter the number 4. Since it's not in the dictionary yet, we add it with a frequency of 1, so count becomes 4, 1. Next, we process the number 5 and add it to count as well, updating the dictionary to 4, 1, 5, 1. Then we process the number 6, which also gets added with a frequency of 1, resulting in 4, 1, 5, 1, 6, 1. Finally, we see the number 5 again. This time, instead of adding it, we increment its frequency to 2, so the dictionary becomes 4, 1, 5, 2, 6, 1. Once we've built this frequency dictionary, we compute the sum of unique elements by iterating through the dictionary and summing up the numbers with a frequency of 1. The number 4 has a frequency of 1, so we add it to our result, making the result 4. The number 5 has a frequency of 2, so we skip it. The number 6 has a frequency of 1, so we add it, bringing the result to 10. Therefore, the final output for this input is 10. For the second example, we follow the same process. We initialize an empty dictionary called count to keep track of number frequencies. Starting with the number 1, we add it to the dictionary with a frequency of 1, so count becomes 1, 1. Next, we process the number 2 and add it with a frequency of 1, updating the dictionary to 1, 1, 2, 1. When we encounter another 2, we increment its frequency, resulting in 1, 1, 2, 2. Then we process the number 3, adding it to the dictionary with a frequency of 1, so count becomes 1, 1, 2, 2, 3, 1. Another 3 appears, so we increment its frequency, updating the dictionary to 1, 1, 2, 2, 3, 2. Finally, we process the number 4, adding it to count with a frequency of 1, resulting in 1, 1, 2, 2, 3, 2, 4, 1. To compute the sum of unique elements, we look at each number in the dictionary. The number 1 has a frequency of 1, so we add it to the result, making the result 1. The numbers 2 and 3 both have a frequency of 2, so we skip them. The number 4 has a frequency of 1, so we add it to the result, bringing the total to 5. Hence, the final output for this input is 5. In the third example, we again start by initializing the count dictionary as an empty dictionary. We begin processing the input array with the number 7. Since it's not in the dictionary, we add it with a frequency of 1, so count becomes 7, 1. When we encounter another 7, we increment its frequency, resulting in 7, 2. Next, we process the number 8 and add it to count with a frequency of 1, updating the dictionary to 7, 2, 8, 1. Then we process the number 9 and add it with a frequency of 1, so count becomes 7, 2, 8, 1, 9, 1. Another 9 appears, so we increment its frequency, updating the dictionary to 7, 2, 8, 1, 9, 2. Finally, we process the number 10 and add it to count with a frequency of 1, resulting in 7, 2, 8, 1, 9, 2, 10, 1. Now, to compute the sum of unique elements, we iterate through the count dictionary. The number 7 has a frequency of 2, so we skip it. The number 8 has a frequency of 1, so we add it to our result, making the result 8. The number 9 has a frequency of 2, so we skip it as well. Finally, the number 10 has a frequency of 1, so we add it to the result, bringing the total to 18. Therefore, the final output for this input is 18. Here, we'll analyze the time complexity of the solution step by step. First, we build a frequency dictionary using the input list nums. This involves iterating through the list once and adding each element to the dictionary. Since dictionary insertions generally take constant time, this step has a time complexity of O(n), where n is the size of the input array. Next, we iterate through the dictionary using count.items. The dictionary contains at most u unique elements, where u represents the number of distinct elements in nums. In the worst-case scenario, all elements are distinct, so u equals n. For each dictionary entry, checking the condition if frequency equals 1 and updating result takes constant time. Therefore, this step also has a time complexity of O, U, which is bounded by O, N, since you cannot exceed N. Combining these steps, the total time complexity of the solution is O, N, as both operations are linear in terms of the input size. Now, let's analyze the space complexity. The primary contributor to space usage in this solution is the frequency dictionary, which stores a key value pair for each unique element in the input array. In the worst case, where all elements in nums are distinct, the dictionary contains U entries, where U equals N. Each entry requires constant space, so the dictionary uses O, U, space, which simplifies to O, N. Other variables, such as the integer result and loop variables, consume only O1 space. Additionally, the input list nums is passed as an argument and does not require extra storage since we are not making a copy of it. Therefore, the total space complexity of the solution is O, N, dominated by the storage of the frequency dictionary. To understand the efficiency of this solution, let's compare it with a brute force or naive approach. In a naive solution, we might iterate through the array nums for each unique element to count its occurrences. This would involve nested loops, leading to a time complexity of O, N squared, in the worst case. In contrast, the given solution optimizes the counting process by using a dictionary, reducing the time complexity to O, N. Now, let's consider the best, average, and worst case scenarios. In the best case, the input array contains only one element, such as nums equals X. Here, both dictionary creation and iteration involve constant work, so the time complexity is O1. In the average case, the elements are distributed randomly with some duplicates. The time complexity remains O(n), because we still perform a single pass through the array and iterate over the dictionary. In the worst case, all elements in the array are distinct, such as nums equals 1, 2, 3, n. Here, we need to iterate through the entire array and process each unique element in the dictionary, resulting in a time complexity of O(n). To mathematically verify the big O analysis, consider the two main loops. The first loop iterates n times, performing constant time operations per iteration, which contributes O(n). The second loop iterates u times, where u is the number of unique elements, also performing constant time operations per iteration. Since u is bounded by n, this step also contributes O(n). Adding these together, we get O(n) plus O(n) equals O(n). Thus, the overall time complexity of the solution is O(n), and the space complexity remains O(n), primarily due to the dictionary storage. One of the most common mistakes when solving problems is misunderstanding the requirements. This often happens when you skim through the problem description without fully digesting the details or fail to account for edge cases. To avoid this, take time to carefully read the problem statement and verify your understanding by working through a few examples. Another issue is relying on inefficient algorithms, like brute force approaches, without considering constraints like input size or time limits. Here, analyzing the problem's constraints is key. Ensure your solution aligns with the required time complexity, such as aiming for O(n) or O log n where appropriate. Additionally, overlooking edge cases is a frequent pitfall. For example, ignoring scenarios like empty arrays, single elements, or negative numbers can lead to incorrect solutions. The best strategy is to explicitly list these edge cases before you begin coding and ensure your implementation handles them properly. Finally, choosing the wrong data structure can derail your solution. If you need fast lookups, for instance, using a set or hash map is far more efficient than a list. Always match the data structure to the operations your solution requires to optimize performance. Off-by-one errors are another challenge you should watch for. These typically arise when array indices or loop boundaries are mishandled. To address this, use clear and descriptive variable names and test your code against boundary conditions to catch errors early. Now, when it comes to interviews, recognizing key patterns and problems is crucial. Many problems are built around techniques like sliding windows, hash maps for frequency counts, or divide and conquer strategies. By practicing these patterns, you'll become better at spotting them in problem descriptions. Also, time complexity awareness is vital. Always justify your algorithm's time complexity during interviews, as interviewers value candidates who understand trade-offs between efficiency and feasibility. Thinking out loud is another powerful tool. By explaining your reasoning step by step, You not only help the interviewer follow your thought process but also create opportunities to catch and correct mistakes before they escalate. Finally, start with a brute force solution if necessary, but always look for opportunities to optimize. Techniques like dynamic programming or memoization can make your solution more efficient and scalable. There are several related problems that can help you deepen your understanding of common techniques. For instance, LeetCode 1, also known as the two-sum problem, demonstrates the use of hash maps for fast lookups. LeetCode 560, subarray sum equals k, explores the prefix sum and hash map pattern, while LeetCode 438, find all anagrams in a string, is an excellent example of the sliding window technique. LeetCode 3, longest substring without repeating characters, combines hash maps and sliding windows in an elegant way. When approaching problems, you might start with a brute force solution. While this is useful as a baseline, it's often inefficient and best suited for small input sizes. Optimized approaches, such as using sliding windows, prefix sums, or hash maps, are more scalable and typically expected in interviews. Divide and conquer strategies are another powerful option, especially for problems involving recursion or when breaking the problem into smaller parts is intuitive, like in binary search. However, it's important to consider trade-offs. For example, while hash map-based solutions are faster, they may require additional memory, so always weigh space complexity alongside time efficiency. Lastly, keep in mind that optimized solutions can be harder to implement correctly. Prioritize writing code that is both readable and maintainable to ensure the best outcomes. Thank you for joining this session. We explored strategies for solving coding problems even when faced with incomplete details, emphasizing structured thinking, adaptability, and robustness. If you found this helpful, consider subscribing for more insights. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!